in the call for my issues.
I've been a basic statistician.
Infected premises, and the black dots are the non-IP culls. Okay. Vaccination in this case, what makes it an exciting epidemic to analyse, is that vaccination was used, so 10K vaccination, implemented on around about day 60 to 64, so roughly 2 months after the first detection. And then most of the dangerous contact, or the non-IP culls I should say, occurred mostly after about day 84. So that was fairly late on during the outbreak, certainly after vaccination. You might see why later. So what I really want to focus on is measuring or evaluating control policy, so measuring vaccine efficacy. Okay, and this is very much at the population level. I'm aware that my definition of efficacy here is not necessarily a vaccinologist's definition of efficacy. Okay, must be borne in mind that the model I will show you really defines what I mean by efficacy. And then also, what was the true extent of the outbreak? So can we actually attribute a probability to each presumed uninfected farm that they are actually infected, we just haven't detected them yet? So they're these occult infections or cryptic infections. Can we then use this information to inform on vaccination strategy, cull strategy, targeted surveillance, etc.? Okay. So, and I construct models to use the data that I have available. So in this particular case, I was given population data, which I think you can think of as explanatory variables. Okay, if you're going to do a risk factor analysis, you have this idea of sort of explanatory variables and a response variable, right? So I can think of population data as being the explanatory variables, the location of each farm as its centroid, the number of cattle and pigs present on the farm, and also the date of vaccination, which I just set to be at some point in the future if the farm wasn't vaccinated. And then epidemiological data are the dates of case detections and the dates of subsequent culls of the farm. Okay? And just to make the point that infection dates are not observed. You don't typically observe exactly when a farm got infected. You might have some idea based on assessments of clinical lesions, but you might not, but you almost certainly won't observe that actual infection event. Okay, so somehow we've got to account for that sensory. So I used an SINR model where farms start as susceptible, become infected, and then after a period of time become infectious. Okay, and then at some point we detect that case, it becomes notified, subject to biosecurity containment, hopefully its infectiousness decreases, and then eventually we'd cull that farm and remove all the infection. Okay, so I consider the farm as the epidemiological unit. Infections are of course determined by the relationships between farms, between susceptible farms and infected farms, and to make the point that these infection times are censored, leading to this idea of occult or undetected infection. So very briefly, and avoiding a lot of the maths, this is my model. So you can think of infected farms pushing infectious pressure onto susceptibles, which happens once this an assumed 4-day time period has elapsed. That's the sort of prodromal phase, and then the farm becomes infected. At some point it's notified, and its infectiousness due to biosecurity is reduced by this factor gamma 2, and then together the susceptibility of a susceptible farm is reduced by a factor 1 minus theta, where theta is the vaccine efficacy. Okay, so I'm saying if a vaccine is 80% efficacious, this reduces a farm's susceptibility to 20% of what it would be without the vaccination. So that's my vaccine efficacy, and then my spatial extent really is governed by a spatial kernel, which I use as a proxy for the sort of unobserved network that occurs between farms that might spread infection. And I want to estimate the decay, or how quickly this kernel decays with distance. So most people, I feel, in this subject think of a model as a simulator, something that simulates an epidemic, okay, given the population data and the parameters. Just to make crystal clear that what I'm about here is taking epidemic data, time series of cases and identity of cases, etc., and working backwards with the population data to work out what the parameters are. Okay, so I'm doing this in a Bayesian context for a number of reasons. First of all is that I can incorporate prior information. And that's quite important, particularly in the early stages of an epidemic where you don't have much data to make inference of. Okay, and it particularly helps to inform things like vaccine efficacy parameters. Then it also gives me a nice, easy machinery to account for this missing data, the censored infection times and these undetected or occult infections. And it's also fully likelihood based, which means we know what we're getting from our model in comparison to some of the approximate Bayesian computation algorithms which are sometimes used for fitting epidemic models, where there's often a question over exactly what the approximate bit means. It's also fast to compute, and my implementation uses modern GPU accelerated techniques so that I can do this in, at the very most, an overnight time frame. So on the day-to-day management of an epidemic, I think one can consider this real-time analysis, conditional on the data coming. The results are then provided as probability distributions which encapsulate uncertainty and, as we'll show, make them extremely suitable for decision-making under uncertainty. So I'm now going to show you some results from the Japan outbreak, and what I've done is analyse this out. from the start, the first case notification, and I'm measuring the vaccine efficacy parameter. Now, there's a wrinkle to this, because, of course, once you vaccinate a farm, it's not immediately immune. It takes some time for the cattle or the pigs to respond to the vaccine and then raise their immunity. So I'm assuming a 4, an 8, and sorry, that should say 14 days, so 2 weeks, what the textbooks say, the time from immune challenge to immunity takes. And so I'm going to effectively sensitivity test my model to this assumption of delay between vaccination and immunity. And I just make the point here that actually results from an epidemic model avoids the bias that you would normally incur in something like a case control study of vaccine efficacy, where because the infections are not independent, okay, probability of me getting infected tomorrow is dependent on you guys being infected, okay, by explicitly accounting for this, we avoid the bias that's inherent in the standard case control studies. So let's assume then that we've got 4 days between vaccination and onset of immunity. This is what vaccine efficacy looks like. So these are my weekly analyses moving from left to right on the graph. This is now casting. So this is what my model's telling me on each of these days. Okay, and you can see that after vaccination started, which was around about day 60, we get a lag, and then the model starts to respond and tell me something about efficacy. And this efficacy seems very, very low. Remember, I'm assuming a 4-day interval from vaccination to onset of immunity. If I assume 8 days, then this vaccine starts to look a bit more promising. So we've gone up to about sort of 60%, something like that in the middle here. Okay, so this is assuming 8 days. Then if I assume 14 days, I get something that looks rather more like a vaccine efficacy of around about 85%. So I think that's worth sort of thinking about, particularly in some of the modelling studies that make hard assumptions on this delay time. Then the second question I want to ask was, well, was vaccine performed in time? Okay, so my model can tell me when it thinks each farm was infected, okay, and so I can work out a probability that each vaccinated farm was actually infected at the point that it was vaccinated. Okay, now we know that about 63 farms got infected after vaccination. That's in the papers. That's fine. And you can see that the model's picking this up by this cloud of points up here. So I'm plotting probability of already being infected when you're vaccinated against the day of vaccination. So most farms vaccinated between day 60 and 64 down here, and you can see that a good few of them have an extremely high probability of already having been infected. So perhaps when the vaccination strategy was put in, maybe it was too late. It wasn't in front of the epidemic wave enough. I'd be interested in comments. So the following question then is, well, was vaccination and or DC culling keeping up with the epidemic? Okay, and we can do this by looking at the spatial distribution of these undetected infections. I've got a video for you just to show you very quickly how the algorithm tracks these undetected infections. One below. Okay, here we go. So undetected infections are in the red, and you can see them moving around in response to where the epidemic's going. The infected individuals, whoops, can we just play that again? The infected individuals are marked in the blue, and then towards the end of the epidemic you'll start to see some of the grey susceptible farms being extinguished as the DC culling policy went into play. So I conjecture from this that the vaccine policy was perhaps implemented too late, or rather too close to the sort of focus of infected premises, maybe we should be considering a rather wider radius of vaccination. Okay. Yes, please. Sorry. Yeah. Two more slides. Oops, no, you don't want to see that. Only if you're interested, you want to see that. Okay. So some conclusions. So methods conclusions then. Well, likelihood inference is fast, and it can provide us nowcast information actually in the space of about an hour for this particular outbreak. For the 2001 UK foot and mouth outbreak, it's about 5 hours. Thanks to NVIDIA, who donated me a very modern GPU, which I think is suitable for epidemic management if we can get the data coming in quickly, and that's something that I'm thinking about at the moment, ways to actually grab in data from the field, pile it into a database for automatic analysis. The joint parameter posterior distribution from the analysis then provides the basis for ongoing forecasting, which we'll talk about now. And if anybody's interested, my GPU code is available here at this web address, which is a GitLab server running back home at Lancaster. If you're interested, please download. I can provide help to compile it on hardware. I can provide help for you to run it on my hardware if you need to. From Japan 2010 then, so vaccine efficacy measurement seems highly sensitive to the delay between dosing and immunity. Okay, of course, vaccine takes time to work, but if we assume a 2-week dose to immunity, then we get an efficacy of around about 85%. Okay? I suspect, in this case, the epidemic escaped the vaccine delivery, so we probably need to think a bit more carefully about how we might optimise vaccine delivery in a more general case. The knowledge of the spatial epidemic extent, so these occult farms, can be used to optimise vaccine delivery and culling. I conjecture, and I've got a simulation study in a paper in Biostatistics in 2012 that shows that actually ranking these farms by their occult probability and targeting surveillance to the highest probability farms is actually a really quite good targeted surveillance policy for slowing epidemics quickly. More precise results would be nice, and just a plea to those of you in the audience who are responsible for collecting data, curating data during outbreaks, negative testing results are as useful as positive testing results. Okay? And that would be really good in the Japanese case. If I had those results, I'm sure I could be far more precise about some of these estimates. So thank you very much.
Okay, thank you. Perhaps it would be good to have a discussion after the next one, and we have a discussion on both of the models. Okay. Then I will ask the next presenter.